Okay, so welcome to my talk, Automatic Application Hardening by Leveraging Container Runtime Behavior Analysis During CI Processes. Kind of a long name, but it's a pretty cool talk. So just a bit about myself. My name is Amit. I work as a security researcher in AppArmor. We are the makers of Kubescape, which is the open source CNCF project. We're doing Kubernetes security. It's a very big open source project, so I advise you to check it out. And usually in cyber talks, before the cyber talk, you're all happy, and then you come to the cyber talk and you hear about supply chain attacks and SolarWinds and Log4j, and I don't know if you saw it just yesterday on the CAPS vulnerabilities that just come out on all Linuxes, and then you're like, oh man, I'm doomed, right? Because I'm gonna get hacked. Well, hopefully after this talk, it's going to be different, because yesterday you probably heard a lot about hacking and cool stuff. So let's see how we can handle this. So the agenda is going to be, first of all, we're going to talk about Kubernetes native policies. We're going to see what kind of policies do we have and how we can use them. Then we can see how we can generate vulnerability posture and policies from runtime behavior of the containers. And finally, we're going to see how we can add it to the CI/CD to make everything automated as we like. So let's understand the threat model that we're dealing with. Let's say you have a Kubernetes cluster, okay, and you have a certain pod, which is a internet exposed pod, right? It's a public facing. It can be a web server. It can be any types of service. So let's say it has two attack vectors, right? So application exploit, if you're running a vulnerable package, a vulnerable image. So an attacker can come from the outside, execute code on your pod, and then he's running code on your pod. Another interesting attack vectors is, let's say it can poison the image registry with some malicious image, and therefore also run code on your pod. Assuming he's running code on your pod, it can do mainly two things, right? So the first one is container escape, and if anyone been in my talk yesterday where we covered some container escapes, so an attacker can escape the container, execute code on the node, and once an attacker is on the node, it has access to the kubelet configuration and secrets and everything, so it's basically game over. And another thing an attacker can do is lateral movement inside the cluster. So by default in Kubernetes, you don't have network segmentation. You don't have too many security mechanisms that prevents attacker from talking to different pods in the cluster, even if there are different namespaces. So you can move laterally, and then from there, it's also a bad thing. And we call this entire thing like the blast radius, right? So what happens when an attacker gets code execution on the pod? Everything else is the blast radius. So this talk is about how we can reduce the blast radius significantly and even completely prevent it. So let's start by talking about vulnerabilities, which covers the first initial access of the attacker. So I guess most of you are familiar with the entire trend of remediating and patching all the vulnerabilities, creating S-bombs, and all this AppSec teams and DevOps teams and developers that are working around the clock to just patch all the vulnerabilities, because it's hard, right? So you have standard tools that are doing an awesome job in finding those CVEs in your images and containers. But the problem is that the average application has about 100 vulnerabilities. And as we all know, that not all of those vulnerabilities are actually dangerous or can affect us or even relevant to our application, because there are a lot of vulnerabilities in software packages that aren't really being used in runtime. So all in all, it's very expensive to manage this thing. So what we did with Kubescape, again, it's open source, so you can check it out. So we created something called Kubescape Relevancy, which basically utilizes eBPF. Okay, we're installing Kubescape as an agent in each of the nodes, so as a daemon set in Kubernetes, for example. And using eBPF, we record all the file activity that are happening in the container. And what it allows us to do is to create something we call filter the S-bomb. So SBOM is the software bill of material, right? Once you have like the SBOM of a container, you can understand all the software packages that are installed in the container, in that image, and then generate a list of CVEs. The problem is that in runtime, let's say you have a Python application that is serving a web server, okay? So it's using Flask or Fast API or something like that, and maybe some 10 other Python packages. But on the container itself, it can be like 70 or 80 Python packages that are installed on the machine, but you're only using half of it. So why should you remediate and patch a CVE that is not even being loaded into memory, and therefore it cannot be exploited, right? It's just dead code on the disk. So we can save a lot of the time. And actually, in our production system, it reduced the amount of vulnerabilities by 80%. So what we can do is to create this filter SBOM and then cross it with the SBOM from the tools like Gripe, for example. And we create something called the relevant vulnerabilities. So you only get the vulnerabilities that are actually being loaded into memory. And I wanted to talk about something that I recently saw, that a lot of people are saying, wait, we can even take this further. So instead of just looking on runtime on the files and giving CVEs for software packages, like relevant vulnerabilities at the package level, right? So this is happening at the package level. Let's do it on the function level. So let's see if the vulnerable function is actually being called. And in theory, it sounds pretty nice, right? Because we can filter even more strictly. But in reality, if you think about it from a security perspective, this is actually kind of a mistake, because let's start with the first point. Most CVEs don't even have the function information. So if you look on most CVEs, you won't find which function is vulnerable. So if you want to scale it up, there are tens of thousands of CVEs. If you want to scale it up, it's not going to scale very well, because less than 1% of the CVEs have this information. And doing it manually requires a lot of work, so you cannot really count on it. But the second problem, which is, I think, the main problem of this idea, is that if you take the way we can do it with eBPF or any other recording tool, is that mostly those tools that are doing things like relevant vulnerabilities, like we do in Kubescape, the way it works is that when the container starts, we record it for like a couple of minutes, because then we can see all the activity that happens on the start, because most of the time, most of the activity happens when the container starts. So if you record all the functions that are being called in the first couple of minutes of the container, it doesn't necessarily mean that the vulnerable function can't be called later. Because if you think about, let's take an example. Let's say you have a web server that has an engine that processes some files. And usually, on the first couple of minutes, or even this is the application intent, it can only process Word documents. Okay, so people can upload Word documents, and the application will process it. But then someone, an attacker or just a regular user even, can upload the PDF to the application. And suddenly, a different application flow is happening in the application, right? So a different application can be called. And if you're filtering vulnerabilities only by functions, you would say, OK, this CV doesn't mean anything to me. I can ignore it. You can just filter out this package. But actually, you are still staying vulnerable. So vulnerability management at the function level, it's actually a mistake. You're filtering out relevant vulnerabilities. And the third bullet, which is more in regarding for remediation, so if you think about it in teams, in developers and DevOps, usually the patches are at the package level, right? So they're not on the function level. So you can't really patch functions of third-party libraries. I would say, though, that when you have function-level information on vulnerabilities, it can really help you to detect when the CVE is happening. So if someone wants to execute log4j, for example, and you can look on the functions, so you can say in runtime, OK, someone is exploiting this vulnerability right now. But for using it to filter out vulnerabilities in advance, this is a mistake. OK, so let's move on to, after we covered the first initial access vector, let's move on to talk about some kernel protection or container escapes. So we have the pod security context, right? It usually contains like the user or group ID. You can add process capabilities and say, is the pod privileged or not? And you can also add seccomp, which we're going to focus on this talk, because we can generate seccomp policies, which are actually a really strong tool. And what we did is we took some CVEs, some of the latest CVEs that are related to kernel escapes, to container escapes using kernel vulnerabilities. And we actually found that if a seccomp profile was in place, those CVEs cannot be exploited. So the thing about those policies, and this is why it's so strong, is that in some way they can prevent 0 days, because, or not prevent 0 days, but prevent them from being exploited, which is more accurate. So if you have those in place, you can prevent those CVEs. A word about seccomp, if you're not familiar with it. So basically, it's a facility in the Linux kernel that allows us to filter out system calls. It has 2 main modes, the first one being strict mode, which will allow your process to execute only 4 system calls. And if your process tries to do anything else, it will be killed. It's more accurate, it's on the thread level, not on the process. And another mode is that you can put filters mode. And this basically allows you to do like more smart filtering. You can load the BPF filter, so we can write some rules, some interesting rules, and then filter by that. And in the recent versions of seccomp, they also added some very cool things like seccomp notifications. And actually, I know that the LXC group is utilizing it to do some cool things with containers and container mounts. So I advise you to read more about this mechanism. So in Kubernetes, we have the option to supply seccomp profiles. And the thing about seccomp profiles is that if you think about it, if you'll go out to your developer and say, can you give me the list of system calls the application is doing? He will look at you, he won't understand what you're talking about. And so it's very hard to generate them. This is one of the main problem of policies in Kubernetes today, is that it's very hard to generate them. So you have something called pre-made seccomp profiles, right? So if you look at the Docker documentation, they're stating, hey, this is the default seccomp profile we're providing with the containers. So this is what comes when you use Docker as your container runtime. Some container runtimes don't even put a seccomp profiles, some do. But the problem about those pre-made profiles is that Docker can't know what system calls your application is going to need, right? So you can assume that the profile that they're providing in advance is over-permissive, because you don't want applications to break over Docker. But for example, they block loading of kernel modules by default, which makes sense. Manual definition is the second way to do it, but it's also very hard because, again, you go to the developer, no one knows which system calls the application is doing. It's basically impossible. And so the best way to do it is to generate from the application behavior. The thing about those policies is that they need to be tailored per the application. And this is what we're going to see how to do today. So also in Kubescape, the same way we monitor files with eBPF, we also monitor system calls. And using those system calls, we can create a custom seccomp profile that you can just apply into your cluster, and we will take care of all the tedious things of like putting the profile on the node and configuring the deployment to fetch this seccomp profile. So you basically get this nice CRD that you can just apply, and it contains all the system calls. So this is how we generate seccomp. The next thing that we're going to talk about is network policies. And we all know why network policies are very important. I hope so. As I said, by default in Kubernetes, you don't have network segmentation, so everyone can talk to everyone, and it's obviously a bad idea. When an attacker gets a foothold on a certain pod, he shouldn't be talking to the databases or access whatever he wants. So using network policies, we can actually prevent lateral movement and data extraction, which is important. But the same problem we have with seccomp. Network policy generations are very hard. Who is maintaining those policies? Who is defining those policies? Because in difference from seccomp, which is very hard to tell which system calls are going to be happening, you can predict which network connection the application wants to do, right? So the developer can say, okay, I need to make a network connection to my Redis server and to my Mongo, and that's it. But then the DevOps team is going to change some things in the cluster. They're going to migrate into different areas. They're going to change the addresses. And then there is the SRE and developer. So it's all mixed up, and you don't know who is maintaining what. So what usually happens when companies try to maintain network policies is that it breaks all the time. And then they get errors in production, in their application, and it's bad. So same as before. Now, instead of looking on files and system calls, we look on the network connections. So again, using the eBPF on each node, we record the network connections and generate the seccomp profiles automatically for the application. This is very cool, and you can just take this network policy, apply it. It also integrates with all the popular CNIs like Cilium and Calico. So it's very convenient. So imagine you have this magic box where you could just throw in deployments, throw in your pods, your applications, everything, and you get out a list of filtered vulnerabilities, network policies, and seccomp profiles. Wouldn't that be great, right? So this is exactly what we did. Now we have continuous, we have CI/CD and also continuous security, which is awesome. So how can you do it? What we're going to do is we're going to, in your CI/CD, create a test namespace. We're going to start the event recording, the eBPF recording of all the events, like the files, the system calls, the network connections. Then we're going to deploy an application. We're going to run tests on the application so we can see how the application behaves on different activities. Then we're going to stop the event recording. We're going to generate those policies, the seccomp profiles, the network policies and vulnerabilities. Then we're going to apply those policies. We're going to rerun the test because we want to make sure those policies didn't break anything. And if everything works, we can just continue with the pipe, continue to commit to the Git. Right? So this sounds like an awesome plan to just integrate it into the CI/CD, and you get out of the box all the policies. So let's see a demo of that. We're going to see the environment setup. We're going to see how we can generate seccomp profiles, how we test it. Same goes for network policies. And the project itself, you can find it here if you want. We're just going to take a look on it. So let me zoom in a little bit. OK, so this is the repo, very simple, quite tiny repo. We have the scripts. So we're going to create a minikube, just a script that creates a minikube. We're going to deploy kubescape, which is very simple. It's just a simple helm command. Very convenient for Kubernetes. And let's dive into how we do each of them. So to create network policies, what we do is we're going to use the hipster shop from Google. So we're going to create a namespace. We're going to download the microservice demo app. We're going to get all the deployments. We're going to apply it. We're going to wait for the deployments to be ready. Then we're going to generate network policies using kubescape for all the deployments. So once kubescape is installed, it automatically generates the network policies. So here we're just fetching them. Then we are going to apply those network policies. We are going to restart the pods in the namespace so they can start using the new network policy. We are going to wait for everything to be ready. And finally, we're going to delete the namespace. So pretty simple. 70 lines of script. Without the nice graphics, you can even make it shorter. And the same goes for seccomp. Very short, very easy, very convenient to use. So let's see a demo of that. So we have a recorded demo of this process. Using the project I just showed you, we're going to create a minikube. OK, we have a minikube in place. Now we're going to deploy Kubescape. So simple helm install, also installing it. Great, so we have Kubescape installed. Now let's start generating some policies. Okay, so now we're creating the network policies. Again, we're deploying the demo app, all those deployments, you can see them on the screen. Now Kubescape is going to take some learning time. Okay, so we're going to record it for some time, and then we're going to generate the policies based on those recordings. So here we're waiting for them to be ready. Then Kubescape is going to learn, and it's going to generate the policies for us. We can speed up some things. Okay, so we're sleeping for 180 seconds. I don't know if you can see it on the bottom. So in those time, the tests of the application are going to run, so we can see the application behavior. We're going to now generate those network policies for the deployments. We're going to roll out the pods to 0. Then we're going to put it back up, so the network policy is going to be in place. And now let's test that it works. So here what we're doing is, I don't know, it's a bit on the bottom, but what we're doing is we're executing into one of the pods, and we're using Python. We're opening a socket into the Redis cart deployment that we also have, and we can see that it failed, right? Because we have network policy. This workload, the load generator, shouldn't be talking to the Redis cart, so the connection failed. Now we're going to delete the network policies. We're going to do the same thing again, and we can see that we successfully been connected. Right, so this is a very simple example how, without a network policy, an attacker can talk to your Redis server, and with a network policy, you just get a free win of preventing the attack. Now let's see how seccomp works. So, same things. We're going to create all the deployments. We're going to wait for them to be ready. We're going to record. Let's speed up. Waiting for all the tests to run. Okay. So all tests ran. We generate the seccomp profiles. So we are downscaling all the deployments. Now we are applying those profiles. We're patching the deployments to use those new seccomp profiles. Wait for them to be ready. Okay. We can see they are running, which is good. They are running with the seccomp profile, so we're filtering out system calls. And now what we try to do is we try to run the echo command inside the load generator. It shouldn't be running. It's probably using a system call that shouldn't be happening. So you can see that it failed, right? So the command failed. Now what we can do, again, delete the seccomp profiles just to prove it. Okay, I don't have it in the video, but if we remove the seccomp profile and do this echo process again, you can see it works. So this is a very cool example. Now we did it on our local machine, but the exact same things can happen in the CI/CD, as we talked about the process of doing it. Okay, so is it time to celebrate? Maybe. But let's talk about caveats and advantages of this approach. So let's start with the bad things first, so we can finish in a good way. When doing these things, first of all, in CI/CD, it takes some extra resources, right? So you need to scale, you need to deploy all of the application, run thorough system tests for everything, so everything can be recorded and we don't miss anything. So this can be it can cost some more money and be time-consuming. And developers don't like when a lot of tools are interfering in their code, in their pull requests, etc. So developers may not like it too much. If you don't have certain test paths, if you're doing tests with an incomplete system, so you're just in your test, you're not testing all the components together, this can break this method, right? Because this method, we need to record all the network activities and all the system calls. So if in your test you don't have good tests, then we're going to miss some things. We're going to do too much of a strict policy, which will probably break in production. But originally, when we wrote it, as a caveat, I just thought, well, that can make them also write some good tests. So two birds in one shot. So write some good tests, and then everything works as expected. And of course, the advantages of this method is that it improves the security posture of your Kubernetes cluster by a ton. If you're applying network policies and seccomp profiles, you will make the attacker life so much harder. You can try it. There are some good CTFs where you can apply those policies, and you can see how you're basically locked. You have nothing to do as an attacker. So this is very powerful. And considerably less vulnerabilities to handle, which touches the first thing that we talked about vulnerability management. It cuts off, as I said, in our production system by 80%, it's massive, and it makes vulnerability management actually possible. You set up it one time you set up this workflow, and then you just forget about it because it just runs automatically, so you don't have to mess with it all the time. And you get out of the box the principle of least privilege applied in your Kubernetes cluster. So everyone's talking about apply least privilege principle, but how do you do it? So here is how you do it. So there are some good and bads into this method, but I think it can work. We tried it. We had some problems with those caveats because we had incomplete system tests in our system, but then it also led us to fixing those systems. And after that, everything works perfectly. So it can work for you. If you want to see it for yourself and play with it, this is, again, the repo. You can scan it. And thank you. If you have some questions, feel free. Yeah, you want to ask? Okay.
You want me to wait for the microphone? Or?
You're loud enough.
Yeah. I was just curious, when inside of that platform, is there any way to set, like, here's the sort of the loosest we'd want to be with those policies, and prevent, as you're doing that monitoring, sort of any of those, I'm just like spitballing, but if there's a syscall that's being made that we would absolutely not want in our policy ever, right? Like, is there any way to do that within that platform, or?
Yeah, so basically, those policies are being generated as CRDs in the cluster, so we can manage them as you manage any other Kubernetes resource, pods and everything. And the nice thing is that you can also pre-made those policies, for example, in your dev environment, and then just apply those policies into production. So we don't even need to have this learning period in the production. So you can review the policies, and if you want to add or remove a system call, it's very easy. Anyone else? Yes.
You said that this slows down CI/CD. How rarely can we get by with rerunning this once we generate the policies? For example, at release level, or I don't know. Is it likely to break day to day once the policies are there and in place, but the application is being, new features are being introduced? How likely are they to change?
So one of the reasons to put this in the CI/CD is that every time you release a new feature or something, you want to make sure those policies aren't breaking. So every time, I would put it like at the end of the release process. So everything is done, it's ready for production. Let's run this CI/CD, get the policies, and then you can apply them, and it won't break the production because you just tested it.
Yeah, so you can't get by with turning off the tests, of course, but is the slowdown the tests themselves, or let's say, is the slowdown the actual policy generation?
So the policy generation, it doesn't slow down the test because it's happened in parallel. So what you do is you install the kubescape daemon set on the CI/CD, and then it in the background, it learns, it installs the eBPF, and eBPF works asynchronously, so everything that the tests are running in the application, and in parallel, Kubescape learns all the behavior, so it doesn't really slow anything. It just, you need the test to run. This thing.
Thank you.
Sure. Yes.
Quick question regarding the granularity of the policies, because many times we have agents within the clusters that require information from the pods to do security scanning, to do all these different things. Is there any granularity on which of a white listing of specific system calls from specific agents, or if you get a system call thrown out, it's not used by anyone?
I would say, there are the pre-made profiles of seccomp, the same as Docker provide. But the problem is that you can never know. You can say, okay, I'm creating a pretty strict seccomp profile, but then it can break a lot of the applications. And you may have even missed some system calls. So you can't really tell, and this is why seccomp profiles should be tailored per the application. It's very hard to predefine anything. Yeah. Okay, I think we're done. Thank you very much. Thank you.